there's this approach to numerical invariance called categorification. So every time you have a number, you try and express it as the Euler characteristic of a collection of vector spaces. You see, so the Euler characteristic is the original example. Categorification of the Euler characteristic is the homology groups. So you take the alternating sum of the homology groups, you get the Euler characteristic. So it seems plausible there's a categorification of this invariant counting minimal surfaces, which, just like the minimal surfaces count J-holomorphic curves, this categorification ought to be related to a 7-dimensional manifold with a G2 structure. So you would cross this with R to get the 7 manifold. So maybe I could talk a bit about that, or I could talk about this idea of counting minimal surfaces in other Riemannian 4 manifolds. So these other guys that are negatively curved. And there's another extension of the idea, which is this 6 manifold. It's not just almost complex, it's actually symplectic. So you can try and extend this idea to counting J-holomorphic curves in a certain class of symplectic 6 manifolds, which look asymptotically like this one. So there's a new class of 6 manifolds in which you can define Gromov-Witten type invariants. So all of these are parts of the project that are still very much in progress. Okay, so now let's get to the history. So the idea of finding minimal surfaces is, of course, extremely old, and I'm contractually obliged as someone who works in Belgium and has now become half Belgian to tell you that Plateau was Belgian, a Belgian physicist, and he asked the question, if you take a closed curve in R3, can you fill it with a minimal surface? And as you all probably know, Douglas and Rado said, yes, you can definitely do this in the 1930s. They proved that it bounds a minimal disk. Any closed curve in R3 bounds a minimal disk. But of course, the disk could have lots of singularities. It could have self-intersections and all sorts. And I think there was a long-running question that said, if you instead take your loop, your embedded circle, to lie inside the unit 2 sphere, then perhaps it bounds an embedded minimal disk. Okay. And this was proved by Burma, Tommy, and Tromba. And the reason why I want to just explain this one result in the entire history of the Plateau problem is because the idea is absolutely essential to everything that's going to come afterwards. So here's what they did. They looked at the space curly C of embedded copies of S1 inside S2. Now, just for the purposes of exposition, I'm going to ignore regularity, but you really need to use Banach space. Not just smooth circles, but there needs to be the right Banach spaces and all the rest of it. But let's just ignore that. Okay? So that's one space, curly C, and then there's curly M, which is the space of embedded minimal disks whose boundary lies in the 2 sphere. Okay? So obviously, if I have an embedded minimal disk, I can send it to its boundary. And that gives me a map, the boundary value map from curly M to curly C. And this is the key fact. So these 2 spaces, curly M and curly C, they're infinite dimensional Banach manifolds. And this boundary value map is Fredholm. And absolutely crucially, so it's index 0, and it's proper. You see, so index 0 means that if you choose a generic point, the pre-image is a 0-dimensional submanifold of curly M. And proper means that it's finite. So you choose a generic circle inside the 2 sphere, and you can count the number of elements in the pre-image. And that's a well-defined invariant of the map, the degree. Okay. I guess strictly speaking here, I've not looked into orientation questions, so it might be that this degree is only well-defined mod 2. Okay. But that's already enough to prove their theorem. Okay. So we have this well-defined degree, and then you can actually compute it. And the reason you compute it is because there's one case in which it's very simple to find all the minimal surfaces. If you take the equator of the 2 sphere, then it's quite easy to show using the maximum principle that the only minimal disk that fills it is just the obvious one that fills the equator sitting inside R2. And there can't be any others. So we've found a point for which this count is equal to 1. So that means the degree is equal to 1. Okay? And if you have a map which is degree is non-zero, then it has to be surjective. Okay? Because if it missed a point, I could have used that point to compute the degree. and I'd have found 0. That's contradiction. Another way of saying it is this properness, you can think of it as allowing you to carry out a continuity argument. You take the loop you're interested in inside curly C, and you join it by a path of loops to the equator. And properness is more or less telling you can follow that path by a path of minimal disks that start at the completely flat, totally geodesic line. Okay. So in this way, they were able to prove that this map is surjective, and so indeed every single circle inside the two-sphere fills an embedded minimal disk. Okay, so that's R3. Now I want to talk about hyperbolic space, and let's start in dimension 3. In fact, let's start in general dimension, because the first result is an n-dimensional result. So there's something called the asymptotic plateau problem. So this is as follows. So you take you look at the n sphere and you think of it as the boundary of hyperbolic space of dimension 1 higher. And then you take a k-dimensional submanifold of n-dimensional sphere, and you ask, is there a minimal submanifold inside hyperbolic space whose boundary is n? Okay. So you want to find M such that the boundary of M is n and M is minimal. And in the 1980s, Mike Anderson proved that the answer was yes, provided we have a sufficiently relaxed understanding of what submanifold is. Okay? So his proof, essentially, you push this boundary slightly into hyperbolic space, you solve the plateau problem there using geometric measure theory, and then you take a limit as the boundary runs to infinity. And this is a fantastic existence result. On the other hand, it doesn't tell you anything about the topology of the bounding surface. It doesn't tell you anything about how many there are. It doesn't tell you anything about whether it's smooth or whatever. You see, so from that perspective, from the geometer's perspective, there are still a lot of questions to be answered. Okay, so inspired by this result that I just explained to you of Bohm, Tommy, and Tromba, Alexakis and Matseo devised a degree theory for minimal surfaces in H3. Okay, so let me just state their theorem. It's very similar to what I just said for Bohm, Tommy, and Tromba. So we're going to have two integer parameters now. We're going to look at connected minimal surface in H3 of genus G, and it's going to have k boundary components. Okay, so then you have this space of minimal surfaces, and they want them to be properly embedded, so they run out to infinity, and the boundary curves lie on the boundary 2 sphere. Connected, so it's important that they're embedded, connected minimal surfaces in H3. And then the space where their boundaries live, I'm going to call curly C K. So that's just K disjoint embedded circles in the 2 sphere. So their theorem is that these two, so this space is already well known to be a Banach manifold, this space of circles. And they prove that the space of minimal surfaces is also a Banach manifold. Again, I'm ignoring questions of Banach norms and regularity and all the rest of it. And they prove that this boundary value map that sends a minimal surface to its boundary curves is Fredholm, index 0, and proper. So again, you can talk about its degree. See, so now for every G and K, I guess this isn't quite true. I've lied a little bit. So you can define this the degree of this boundary value map. You see, so in fact, these spaces CK, as K goes bigger than 2, they're no longer connected. So there might be more than one degree. You see, so this isn't quite right. But for each connected component of CK, you choose an L that's generic, and you count the number of points inside the pre-image. And there's a way of putting signs on these points so that when you take the signed sum, you end up with a number that is an invariant of the connected component. Okay. And there are 2 degrees, or at least one value of K for which you can compute all the degrees. And that's precisely for the same reason as before. So when you've only got one boundary curve, you see, there's only one component of CK, and you can just take it to be the equator in the two-sphere. And then there's a unique minimal surface in H3 that fills that in. It's just the totally geodesic copy of H2. And there are no others. And you can prove that by the maximum principle. So then we know that genus 0 minimal disks there's one of them. And if you take the count, the signed count of higher genus surfaces with one boundary component, the answer is 0. See? You might be a little bit worried because, well, no, let me not say that. Okay, so for all higher genuses, the answer is 0. Okay. So now I want to explain a nice set of examples that really show that this notion of signed count, okay, that's really important. And these are Mori's hyperbolic catenoids. So this Mori is not the Mori of Bend and Break, the Fields Medal winning Mori. It's a different Japanese mathematician with the same name. So this is my picture here of a hyperbolic 3 space. And everything is rotationally symmetric. So you're supposed to rotate this whole picture around the axis going from the north and south pole. Okay. So this green circle on the boundary, that just becomes the bounding 2-sphere. Okay. And what we're interested in is minimal annuli, okay, that fill lines of latitude. See? So let's start with these two. These two dots here, the red ones, they correspond to a pair of lines of latitude that are quite close to the equator. Okay. And you can ask what minimal surface fills that pair. And then you can show that the minimal surface has to also be circularly symmetric and that it solves an ODE. And now you can solve the ODE and you get 2 solutions. And the reason is that hyperbolic space, there's lots and lots of volume near infinity, exponentially much somehow. And so there's 2 ways to minimize area. You can run as quickly as possible into the middle to escape this hugeness near infinity, but then you pay a price because you've run a long way. See? Or you don't run very much at all. See? Then the whole surface is in a bit where it's huge, but it looks smaller from this Euclidean perspective. See? And it turns out there are 2 such solutions, the small one, the one that's near infinity, and the one that runs all the way in. And now you ask, what happens to these solutions as you move the circles of latitude further apart? See? And what happens is the innermost one moves outwards and the outermost one moves inwards. And then there's a critical value at which they coincide. And then above that, there are no solutions at all. See? So what's happening is that here we have a generic pair of circles. And there are 2 solutions. One comes with a plus and one comes with a minus. And as we move to the purple situation, that's non-generic. There's only one solution, but we shouldn't be using it to compute the degree anyway. And then above that, the plus and minus have cancelled each other and disappeared. Okay? So this proves that the degree of genus 0 surfaces with 2 boundary components is 0.
Where do you know from that these are generic?
Well, what's definitely true is if there are no solutions, that's generic, because it's an empty set of conditions to check. I think it more or less comes down to the fact that they deform. These guys will deform as circle invariant guys. So because the solutions are all circle invariant, genericity is more or less a circle invariant statement.
Okay.
It's true. I have
before already, like with the equator already, because you also don't know that the equator.
The equator is not. The equator is. The equator on its. Oh, how do you already know the equator is generic? Yeah. Right. So it's the linearization of the statement. There's a unique minimal surface that fills it. Okay. It's an index 0 problem. So what you need to prove is that the kernel is trivial.
Okay. I see.
Okay. So I was interested in these degrees, and my PhD student Teen and Guyan came up with a fantastic proof that actually this kind of behavior for these Mori catenoids is generic. It's not generic. It's universal. It's what happens in all of the situations except minimal disks. Okay, so he was able to prove that no matter what situation you consider, if you've got more than one boundary component, then the degree vanishes. And his proof is very similar to this one. I mean, this one passes through symmetries and ODEs, but the idea is that as you push one of the boundary circles a long, long way away, the minimal surface stretches more and more, and at a certain point, it just can't support itself anymore and it disappears. See, so that was more or less Teen's idea here. You have your boundary circles on the sphere, and you take one of them and you move it till it's very small and a long, long way away from all the others. And then if you push it sufficiently far away, you're able to produce a contradiction to the existence of any minimal surfaces at all. So there's a configuration of these circles in which there's no connected minimal surface that fills them. Okay, so now let's come to a clean statement of the main theorem. So I'm going to take a compact oriented surface of genus G, that's my sigma, and the boundary has k components, and I'm going to write B bar for the closed unit ball in R4. And here's my moduli space. So my moduli space is made up of pairs, F and J, modulo and equivalence. So F is a map from the surface into the ball, closed ball, and the map should be C2 alpha. I mean, I'm really not going to place any emphasis at all on the Banach norms and all the rest of it, but it's crucial that the number 2 appears here. Everything goes wrong if you put 1 or 0, okay? It really needs to be 2, and you'll see why, hopefully. The alpha's just there so that we can use elliptic regularity. Okay, so these guys ought to be proper in the sense that the pre-image of the boundary of the ball is just the boundary of the surface. You see, so it's really the picture you have in mind. You've got this. If I use the half space model for hyperbolic space instead of the 4-ball model, you have a surface that really does sit on the boundary of infinity. Okay. Now, what's this J? This J is a conformal structure on sigma, making it into a Riemann surface. Okay. And I'm going to ask that this map F be conformal. In other words, weakly conformal. So if I pull back the Euclidean metric from B bar, I get it's conformal. It's up to a fact. It gives me the same conformal structure as J. But I'm not saying there are no branch points. There can definitely be branch points. And the next thing that I want is that on the interior of sigma, these interior points, they're sent to the interior of the ball. And on the interior of the ball, I have the hyperbolic metric. So I can ask for F to be harmonic with respect to this hyperbolic metric on the interior. Okay. So this is a moduli space of conformal harmonic maps. And then this equivalence is just 2 are related if they're pulled back from each other by a diffeomorphism of the appropriate regularity. Okay, so you have to pull back both the conformal structures and the maps. See, there's obviously an action of the diffeomorphism group on this space. So let's divide by that. Okay. And well, this is supposed to be a talk about minimal surfaces. And the point is that this is an old classical fact, which is that conformal plus harmonic means that the image is minimal, at least where it's smooth. Okay. So there's a very important difference with 3 dimensions, which is that we have to allow branch points. You see, if you look at a surface in 3 dimensions, it's codimension 1. So if you move it around in the world of minimal surfaces, it won't self-intersect. It can't touch itself by the maximum principle. And that means that it also, the infinitesimal version of that statement is it can't pick up branch points, you see. But 2-dimensional minimal submanifolds in a 4-manifold, they definitely can become singular. It's almost guaranteed somehow if you look at big enough families. You just got to think of complex curves in CP2. So you take a family of complex curves in CP2, and unless you've been extraordinarily lucky, there'll be one that has branch points or singularities. Okay. So we have to allow these branch points. And if you look at the work in the case of Boehmer, Tommy and Tromba, or Alexakis and Matseo, they're looking at hypersurfaces that are smooth, and so you can parameterize nearby hypersurfaces in terms of graphs, sections of the normal bundle. See? Whereas here we don't have that option, because if we have a minimal surface with a branch point, it's not even locally a graph itself. Okay? So we can't use submanifolds, we have to use maps. We have to parameterize the minimal surface and deform the map. Okay? So that's why we've chosen this approach of conformal harmonic maps rather than minimal submanifolds. Okay, so what's the next statement? The next thing we need is this space CK. So this is where the boundaries live. So the boundaries are just K different circles, disjoint circles embedded in the 3-sphere. Okay, so I want these. I didn't say that up here actually. I should have said it. So F is an embedding on the boundary. Okay, so we're allowing branch points in the interior, but it's absolutely essential that the boundary be embedded. Okay. So now we have this space of embedded copies of embedded circles, K copies of the circle embedded in S3, and the embeddings will be C2 alpha because F was C2 alpha. And this is just K component links, you see. So the connected components of this are just what knot theorists study. And here's the theorem. Can I fit it all on one page? Yes, okay. So first thing to say is that this moduli space of conformal harmonic maps is an infinite dimensional Banach manifold. Okay. The next thing to say is that this boundary map that sends a conformal harmonic map to its bounding submanifold, to its boundary, is Fredholm index 0. Okay. So you might hope to be able to count. And if you look at minimal disks, just maps from the disk, conformal harmonic maps from the disk, then this guy really is proper, genuinely proper. Okay. When the surface has higher genus or more boundary components, then things can become complicated. And it's not proper anymore. And I'll explain why in a bit, but it's very similar to this statement about families of complex curves inside CP2. So there's a bad set inside the space of links. There's a bad set B. And what you need to do is you need to avoid B. And if you avoid B, then the map is proper again. And I'll explain what B is later. And the absolutely crucial thing about this B is that it's codimension 2. Okay. So I'll explain why that's important right now. So these four things together mean that for each component of the space of links, so for each isotopy class of link, and for each choice of genus G, you can define a degree. So you take a generic point that's not bad. You look at the pre-image, okay? Because it's Fredholm and index 0 and the map is proper away from B, that's a finite set. There's a way to ascribe a sign to each of the points in that finite set. You take that signed sum and you get a number. And that number only depends upon the connected component of the space of links. It doesn't depend upon the specific L you chose. So the point is that if you have two different L's in the same isotopy class, you can join them by a path. Okay? And then this degree will be constant along the path, unless you hit the bad set, because there you lose properness. So some minimal surfaces might disappear, or some new ones might appear. See? And that's okay though, because the bad set's codimension 2, so you can always walk around it. It's not like a wall in the space of links. It's got codimension 2. See? So there's two pictures. This is the space of all the links. Imagine that was the bad set. You might have trouble joining L1 to L2. You'd cross the wall, and so the invariant would jump. On the other hand, we're in the situation where the bad set is codimension 2, so you can just walk around it. Okay, so that's why codimension 2 is essential. Okay, so as I said in the very beginning, there's only one situation in which I genuinely can compute the answer to what this invariant is, and that's when you take the unknot, the simplest case. So for the unknot, you can think of it as the equator in the equatorial S2 of S3. Okay? And because the equatorial S2 bounds a totally geodesic copy of H3, it follows that any minimal surface that fills this unknot actually has to fill it in H3. See, the minimal surface can't move out of H3 into the whole of H4 because of all the symmetries involved. And that means we know all the minimal surfaces that fill it. There's just the totally geodesic copy of H2 and no others. See, so we can compute the genus 0 invariant of the unknot is 1, and all the higher genus invariants are 0. Okay, just like Alexakis and Matseo had. And a consequence of this is that if you take any unknotted circle on the 3 sphere, no matter how wiggly it is, as long as it's C2 alpha, it must bound at least one minimal disk inside H4. Because if it didn't, you could use it to compute the degree and you'd get the answer 0. And that's a contradiction. See? So even just this one simple computation gives a new theorem about minimal surface, minimal disks in H4. Okay? No matter how wiggly and messed up your unknotted circle is, there's definitely a minimal disk which it bounds. Okay, so I'm not going to go through the details of the proof, obviously, but I want to give you some of the ideas.
But Joel, I guess you need genericness, don't you?
No, you don't, because if it didn't fill anything, then it would be generic, because it's an empty set to check.
Okay.
Yeah. You can think of, if you think of the continuity method, genericness is like saying the openness part applies, and properness is saying the closed part applies. So you take a generic path that joins your guy to my guy, to the unknot, and use the continuity method. Okay, so let me explain some ideas in the proof of properness, just in the simple case when we're talking about conformal harmonic map from the disk. Okay, so I've got a conformal harmonic map from the disk, I've got a sequence of these guys, and the boundary is independent of the sequence. You see, so the boundary is constant, and what I want to show is that a subsequence converges. Okay. Did that make sense? There's a sequential compactness. You take a sequence of maps from the disk, all their boundaries are the same. Okay, and I want to know that the maps converge, a subsequence converges. And what are the things that can go wrong? Well, one of the things that you might imagine can go wrong, here I've drawn it. So here's the first minimal disk. And then as we go along in the sequence, a little leg is coming out. And the leg is trying to run out to infinity to create a second boundary component. See, if it could get there, then in the limit, we'd have a minimal surface that filled 2 circles, and that would be terrible news. Okay, but it can't happen. And the reason that it can't happen is because it can't push through a horosphere. So the horospheres are the horizontal copies of R3 inside the half space model. See, and it can't touch one of these from the inside by the maximum principle, okay? Because they have the mean curvatures in the right direction for these 3-dimensional spaces. Not just the mean curvature, the entire second fundamental form. Okay, so that's ruled out. See, this was one of the first things that made me think this problem was tractable, because if you've got experience of J-holomorphic curves in symplectic field theory, this is exactly what happens. See, you're able to rule out this new boundary components appearing, and that's the starting point to the whole compactness theorem. Okay, the next thing that's very important is an idea due to Anderson, which is this notion of convex hull. So what do I do? So the blue curve here is it's just a minimal disk that fills, this has nothing to do with disks, but it's just to do with minimal surfaces, but let's talk about disks. So I've got a minimal disk, and over here, I have a totally geodesic copy of H3, okay? And the point is that, so that the boundary is a 2-sphere inside R3. And the boundary of my minimal surface lies entirely outside that 2-sphere. Then Anderson proved, and it's a simple thing to show using the maximum principle, that means that the whole minimal surface lies outside the totally geodesic copy of H3. Okay. So why is this useful? So now let's just imagine the situation in 3 dimensions because it's easier to draw. So the boundary is now R2, and we're looking at minimal surfaces with a fixed boundary curve. So here's my boundary curve. And all the way along this curve, I've drawn circles that are tangent to the curve, okay? And that are all quite big. And each of these circles bounds a totally geodesic copy of H2 inside H3. Okay? And the minimal surface with this boundary has to lie outside these hemispheres. See? So the first thing you can see is that the minimal surface arrives at right angles. It meets the boundary at right angles, okay? But the second thing you can see is that you've got C0 a priori control of exactly how it arrives, you see? It can't come in very, very narrowly and then suddenly kink, because you could fit a big enough copy of H2 inside to get a contradiction, you see? And the same thing's true when you move to 4 dimensions. Now these circles, they become 2 spheres, and yet they have to wrap all the way around. You know, you have your curve and you have these 2 spheres that wrap all the way around. I have no idea how understandable that picture is. Okay, so it gives you a priori C0 control of the surface, the way that it runs into the boundary. And that's absolutely essential in the compactness. But of course, here I needed the boundary curve to be C2 so that I could fit nice. I know I've got a minimal size of circle that's tangent to it, you see. If the curve was only C0, there'd be no hope, or C1, you see. So that's why 2 is essential. And indeed, I think there are examples of where these compactness results completely fail for C1 boundary curves. Okay, so that's the geometric input. And now there's a very important analytic input, which is so simple as to be almost embarrassing. See, so normally when you're counting J-holomorphic curves, you need to use symplectic geometry and all of that. But it turned out that in hyperbolic space, we didn't need it in the end. And here's the reason. So if you take one of these conformal harmonic maps and you put the hyperbolic metric on the domain, okay, then you can check that the energy density of your map converges to 1 at infinity, independent of I. There's no need to consider it. It's just true for any of these conformal harmonic maps. The energy density tends to 1 at infinity. See, it doesn't blow up there. And then you can just look at the Bochner formula for harmonic maps. And there are 2 terms. One sees the curvature of sigma and one sees the curvature of H. And the curvature of H, at least when you're conformal, the curvature of H is a term that helps you because the hyperbolic space is negatively curved. So you can prove that in fact, the energy density is uniformly bounded. See, so these conformal harmonic maps, they can't bubble. And you kind of knew that already because if they bubbled, there would be a minimal sphere in H2, in H4, and that can't happen, of course. See? So if you put together these arguments, the 2 geometric pictures help you ensure compactness near infinity, and this helps you ensure compactness in the interior. So now it's probably quite plausible that the properness result's true, at least for disks. Okay, so the problem with the description that I've used, this conformal and harmonic map description, is that harmonic itself is an elliptic equation. So when you stick conformal on the top, it looks overdetermined. See? So how do you get around that? Because we want to prove Fredholm results as well as compactness results, and the Fredholm results will need elliptic theory. See? But it's okay because we can rewrite the equation as a first order elliptic PDE. Okay? So this is very similar to, it's a 4-dimensional version of Weierstrass's theorem, that if you take a minimal surface in R3 and you look at the normal, you look at the Gauss map, then that's anti-holomorphic. See, so I've turned the minimal surface equation, passing through the Gauss map, it becomes a first order equation. Okay, so I'm just going to briefly explain how this goes. Okay, so what's the twistor space of H4? So you fix an orientation on H4, and then at each point P, so P is a point in H4, I look at the the different ways of making the tangent space at P into a complex vector space. So I give myself a linear J, which is multiplication by I. So it squares to -1. I want it to be orthogonal, so it preserves the metric. And then a J will give me an orientation because it makes my tangent space look like C2, and C2 is oriented. See? So did it agree with my original orientation or not? If it didn't, I throw it away. If it did, I keep it. Okay? So that's the twistor line at P. And you can check it's just a copy of the two-sphere. You do this for every single point, you get a family of two spheres parameterized by H4. Okay? So it's a two-sphere bundle over H4 called the twistor space. And you could do this for any oriented Riemannian 4 manifold, but let me just stick to H4 for the ease of exposition. And this Z, it's actually an almost complex manifold. Okay, so it's an almost complex manifold in two different ways, naturally. So let me explain how that goes. So tangent vectors to Z, they come in two types. There are tangent vectors that are tangent to the fibers, these copies of S2, they're vertical guys. And then the Levi-Civita connection of H4 will give you a horizontal complement to the vertical guys. See, so the tangent bundle splits as vertical plus horizontal. And the vertical space, V, is tangent to a two-sphere. And we know how to multiply by I on tangent spaces to the two-sphere. So we have a complex structure on the two-sphere that gives us an almost complex structure on V. So to complete it, we need to find an almost complex structure on H. But there's a tautological choice, because each point of the twistor space is a choice of almost complex structure on the tangent space downstairs. And the tangent space downstairs is the same thing as the horizontal space. They're isomorphic, canonically isomorphic. So that gives us this kind of tautological choice of J in the horizontal directions. So now I can add it to my J in the vertical directions to get a J overall. Okay. Or I could subtract it. You see, there's a choice of sign that I use in the horizontal directions. So that gives us these two different almost complex structures. So the one with the plus sign, that was basically discovered by Penrose and then further exploited by Atiyah, Hitchin, and Singer. And this is an entire subject called twistor theory. And what's interesting is that this guy, this J, although my description of it made it look like it depended upon the metric through the Levi-Civita connection, actually it only depends upon the conformal class of the metric. And it turns out that this J is a genuine complex structure when part of the curvature tensor vanishes, part of the Wahl tensor vanishes. Okay? But we're not interested in that case. We're interested in the minus case. And the minus case was introduced by Eales and Salomon, and it is never integrable. Okay? But why are we interested in this guy? We're interested in it because of its relationship with minimal surfaces. So this is the analog of the Weierstrass theorem that I was explaining. And in the Weierstrass theorem, the Gauss map's anti-holomorphic. You see, for a minimal surface, the Gauss map, minimal surface is an R3, the Gauss map is an anti-holomorphic map from the surface to the sphere. And that anti-holomorphic is exactly this minus here. Okay? If you prefer, you could put a minus in front of the whole thing, and then you'd have a minus on the spherical part. Anyway, so what did Eales and Salomon prove? It's this four-dimensional analog of the Weierstrass correspondence. So you take a J-holomorphic curve in your twistor space with this J minus, then you can project it down to the base. And that projection downstairs is conformal and harmonic. So in fact, the image is a minimal surface, at least where it's smooth. Conversely, if you have a conformal harmonic map, then at least away from the branch points, you can lift it in a very simple way. So if you have a point sigma, the image of the tangent space at that point is a two-dimensional subspace of a four-dimensional space. And it's not hard to check that there's a unique JZ, which makes it a complex line. So that explains how to lift your sigma up into the twistor space. ignoring the details, the result is that you have a one-to-one correspondence between J-holomorphic curves in the twistor space, at least ignoring the copies of the fibers, and conformal harmonic maps to H4. Okay? And this J-holomorphic curve equation is elliptic. See? So by passing to this analog of the Gauss map, we've turned this seemingly overdetermined system of equations into an elliptic PDE of one order less. And I should just say that this works for any oriented Riemannian four manifold, not just hyperbolic space, this correspondence. And you should be thinking that this invariant that I've just described of counting minimal surfaces, it's actually a Gromov-Witten type invariant. So Gromov-Witten invariants count J-holomorphic curves, and that's what we've done here. So that this was really my original motivation, to try and understand these Gromov-Witten invariants of this hyperbolic twistor space. It was only afterwards I realized that I was secretly doing knot theory. Okay, so I'm now going to quickly skip over something which is technically quite arduous. So there's a very important difference with the standard situation in Gromov-Witten theory. Now you're used to elliptic PDEs where the symbol is an isomorphism, and that's not true anymore in this setting because of the following thing. When you run to the boundary of the twistor space, the almost complex structure becomes singular. In the same way as when you run to the boundary of hyperbolic space, the metric becomes singular. It has like a double pole as you run to the boundary. If you think of it as dx squared plus dy squared over y squared. You see it's got this double pole. Something similar goes wrong with the J. And if you look at what that means for the J-holomorphic curve equation, you see that the symbol vanishes on the boundary of sigma. So it's uniformly degenerate PDE. So you can't just pick up your favorite book of elliptic boundary value problems and use all the results, because all of them need the symbol to be uniformly invertible all the way up to the boundary. Okay? But fortunately, there is a big machine that has been invented to deal exactly with this sort of problem, which is the zero calculus of Rafe Mazzeo and Richard Melrose. So by adjusting and manipulating and using all of their results and carefully setting the problem up in the right way, you can prove all the Fredholm theorems that you need. And that's how you can show that this moduli space of minimal surfaces is smooth and that this boundary map is Fredholm. See, so I can say it all in 6 lines, but actually that was a several month-long headache for me to write down precisely all the details. Okay, so now I want to just say a few words. I've only got 5 minutes left. So let me just try and explain what this bad set is, okay? So there was a failure when you looked at minimal surfaces that weren't just the disk. There was a failure of properness, and we can now understand what that is, you see? So if you remember the original definition of this M, it wasn't just the map that could move, it was also the conformal structure on the surface, you see? And the space of conformal structures isn't compact. You know, a Riemann surface can develop a node. You see, like an essential circle that collapses to a point. So here's my picture of what's gone wrong for a genus 1 minimal surface. It's pinched to a node. You see. So as I move around in this space of minimal surfaces, I might encounter nodal minimal surfaces. Okay. I don't want to count them, that's hard work. So we can now understand what's gone wrong, you see. So this nodal minimal surface, if you look carefully, it's a J-holomorphic map from the disk, and I've just got 2 points that are sent to the same point in Z. Okay. So the bad limits of genus 1 curves are minimal disks that self-intersect in the twistor space. Okay. And now you can understand why this is a codimension 2 phenomenon, because the J-holomorphic disk is a 2-dimensional submanifold of a 6-dimensional space. So the condition that a curve meets that a 2 manifold meets itself in 6 dimensions, 2 manifold plus 2 manifold, that's 4 dimensions in 6 ambient dimensions. 6 minus 4 is 2. You You see? So it's a codimension 2 phenomenon. And in this way, you can prove that the set of knots that bound these sorts of minimal disks is codimension 2. Okay, so to prove this properness result, that's what we have to do. We just have to avoid those knots that bound these minimal surfaces of lower genus, or these J-holomorphic curves of lower genus that self-intersect. Okay? And that's a codimension 2 phenomenon, so we can just happily throw those away. We already threw away guys that weren't generic anyway, so let's get rid of these ones too. Okay, that's probably a good place to stop, seeing as I've only got 2 or 3 minutes left, and any one of the other things that I was going to say would take much longer. So let me stop there, and I'm ready to answer any questions you might have. Thanks.
Thank you very much, Joel. It was a wonderful talk. And well, are there questions? We have plenty of time for questions. Yes?
I would like to ask one, if it's...
Yeah, please.
Andre, yeah, thanks for the talk. So you've mentioned that there's a big difference between the C2 case and say C1, and that it happens on the level of this convex house of Anderson, so that you have some minimal surfaces which approach the boundary at some very different way. So can you say a little bit more about it?
I'm not sure I can, because I've focused almost entirely all my energies on the C2 case. I know that I gave this talk in front of a different audience in which there was someone who was a specialist in minimal surfaces in hyperbolic space. And as soon as I wrote down this statement, they were like, no, it's not true. There are counterexamples, and their counterexamples were all C1. So, but my argument definitely only works in the C2 case, so that you can fit in these totally geodesic H3s, you see. I didn't, until I gave that other version of the talk, I didn't know whether this was an essential feature of the problem, but it definitely very much appears to be.
Thanks.
I mean, you know from Anderson's theorem that whatever curve you take, is that right? I can't remember. He writes literally for submanifolds, but it's almost certainly possible to find C1. I mean, for example, if you took a square, that's just C0, right? It's got 4 corners. It will fill a minimal, there'll be a minimal, take a square in R2, it'll fill a minimal disk in H3. I'm very confident.
Yes. So that's why I'm wondering, so where the problem appears, but yeah.
But if you start to wiggle the boundary more and more, you might find something strange happens. But it's not that the surfaces don't exist, it's that you don't have properness.
Yeah. Okay, thanks.
I'll try and think of if I can find a better idea of what goes wrong. I'll let you know.
Okay, Gilles Courtois.
Hello, Joel.
Hello.
Are there any relation between your counting invariant and other classical not invariants?
Almost certainly, it's impossible to believe I've discovered a new not invariant, but it seems like quite hard to prove. It'd be very exciting if it was equal to one of the classical not invariants, because then it would be easier to compute it, you see.
The way to compute this.
Yeah. So that was the second part of the talk, which I knew I wasn't going to have time to do. So the idea is to try and prove a skein relation, to try and understand how the count of minimal surfaces changes when you push one strand of the knot or link through another strand, you see. And so there's one invariant, which is the genus, but there's also another, which is a bit like the normal degree of the surface. So if the surface were compact inside a 4 manifold, you could just ask what's its self-intersection number, and that would be another topological invariant. You have to work a little bit more carefully because it's a surface with boundary. But you can still come up with some analog of the normal degree. So there's 2 integer variables. So it makes you think it's probably a 2-variable polynomial invariant. So the integers are the powers, this G or Euler characteristic of the surface and this normal degree. They're the powers of your 2 variables, and then the coefficient is the number of minimal surfaces that you counted. So now the natural guess is, well, what's the most famous 2-variable not polynomial? And it's the Homfly polynomial. And in some situations, we can check that it's true. that if you count the surfaces in the right way, you get the Honfly just by observation. See, so the only ones we can do is the unknot and lots of unknots. There we can get it to work perfectly. But for the Hopf-link, we almost get the right answer. We've got a good guess at what the answer is for the minimal surfaces that fill the Hopf-link, but it doesn't quite, we can't yet massage our definitions to make it agree with Honfly. So it's, if I had to bet, I would say that secretly a Honfly polynomial is hidden behind here somewhere.
Okay, thanks.
Alex, you have a question?
Yes, he can't speak. I can read it in the chat. Can I think of a generic uniqueness statement for minimizers and or with fixed energy? So I guess not. I mean, if you know from Anderson's work that there is an area minimizing minimal surface that fills a given boundary curve. So you're asking if I have a conjecture of the following statement for a generic boundary value, there's a unique area minimizing surface that fills it. Yeah, I don't know. The energy is infinite is one problem. The energy and the area are both infinite. Yes, I've thought about normalizing the energy and normalizing the area and all of these questions, and yeah, I'm not sure that this framework is set up to deal with it, is the best I can say, really. It's a natural question, but it's not one that I've been able to make progress with. I'm sorry.
He can't speak. Maybe he's in a train. I don't know. Yes, he's in a train. That's all. Are there more questions?
If I can, if you allow, Gerard.
Excuse me?
If you can allow, I would like just to ask one question.
Sure, of course.
Yes, of course.
Yeah, I would like you come back just in a comment in the nice picture you drew about the Eurocycles and the fact that in the boundary of H2 manifold, the mass is going stronger and stronger when you go through the boundary, by the boundary, and get close to the boundary.
You mean this picture I drew of the Mori?
Well, Eurocycle and things like that. Well, we'll come back to Mori, but there's one you show with a lot of colors. Yeah, this one.
Okay. Yeah, I mean, yes.
Yeah. It was like an evolution from the red ones to the purple ones.
That's right.
You know, using the fact that the mass is more important when you go by boundary.
Yeah, I guess that was just my heuristic explanation for why you might find two different types of solutions, but it's not a proof, and it certainly doesn't appear anywhere in the proof. The proof is
quite enough, but to understand to see the way you perceive it.
So
at some point you said that for the purple one,
yes,
it was going to give us a contradiction of something like that.
So the idea is that when the two circles are very, very close, these red ones, there are two different solutions. There's a kind of inside one and an outside one. Okay. Where they've made different life choices. This one has decided to run all the way into the middle, and this one has decided to stay close to the boundary. And as
this one will run slower.
Yeah, and as the circles move out, the one that runs into the middle doesn't run quite as far because it's got to come back a long way. And the one that doesn't run so far runs a little bit further than it did before because it's still got quite a big distance to make between these two circles. And at a critical distance, the inside solution and the outside solution coincide. And you only have one solution to the ODE, one minimal surface. And then when you go beyond that, there are no solutions at all.
Okay, cool. Okay. So I can understand now why you call them hyperbolic catenoids.
That's right. If you do the surface of revolution, this looks like a catenoid.
Yep. That's it.
Yeah, absolutely.
Okay, all right. Thanks very much.
I mean, I think something similar happens in R3. There's kind of there's the stable catenoid. If you take two circles, there's a stable catenoid. And there's also some very strange thing that comes out here. If you just try and solve the ODE, you get a different solution that you never see in reality because it's completely unstable.
So Joel, there are also these two disk type solutions, I guess.
That's right. That's right.
So that's the one unstable catenoid in the middle. That's the same as in a Euclidean space.
Yeah.
You have two minimizers,
and
then you have an unstable one in between.
That's right. But this is also a very important point because so my invariant that I described here, I only counted connected minimal surfaces. And then after Gilles' question, I started talking about Homfly. And if you want to talk about a skein relation, you absolutely have to include disconnected surfaces as well. See, so in writing down some invariant for this pair of circles, you'd want to see these two disks as well. But that's all you'd see because there are no annuli. But you see, it's essential. Otherwise, there's no hope of getting a skein relation. So to upgrade this to some minimal surface polynomial that's equal to Homfly, you definitely need to also include disconnected minimal surfaces. And you also, it doesn't matter when components intersect, you see, because there's always this question, am I treating my minimal surfaces as currents? You see, if I have an intersection, then if the intersection isn't at the right angle, it might not be minimal as a current anymore. You see? You look confused, Felix.
If you have two smooth guys intersecting, the current doesn't see it.
Is that right? Yeah. Okay, great. That's good news. Is there not some theorem about two planes in R4? If they intersect with the wrong angle, then they're not minimizing near the intersection.
They're not minimizing, but they're still minimal.
Ah, okay. Yeah, you're right.
They're not minimizing, but they're still minimal.
Yeah. Okay, good. That's good.
Since you're not working with minimizing, you don't care about minimizing, you just want minimal.
Then that's good. Okay, good. Even better.
You're not working with like Lagrangian surfaces where you have to have minimizing.
Yeah, no, that's right. Yeah, this is where my confusion came from reading papers about smoothing intersections of Lagrangian minimizing guys.
Yes, but without minimizing, you lost.
Okay, good point. Thank you.
Just a last one, a quick one. How does the J structure? What does the J structure do better than the Riemannian case? If you just minimizing in the Riemannian metric normal.
You mean why have I moved to J-holomorphic curves?
Yeah.
So there's two answers. The first answer is that because I had to parameterize the minimal surfaces, you can't just look at submanifolds because they're not smooth. They needn't be smooth. They could have branch points.
Yeah, this I got it.
So in order to get a Fredholm theory for the deformations, in order to understand the deformations, you have to parameterize them. To parameterize them, you look at conformal harmonic maps, but conformal plus harmonic on its own isn't elliptic. Instead, you should lift to the Gauss map and it becomes an elliptic PDE, which is the J-holomorphic curve equation. Yeah. The second reason is that secretly, this could be the starting point of a new type of symplectic manifold where you can make sense of Gromov-Witten invariants. You see, you take a symplectic 6 manifold, but near its boundary, it looks like the twistor space of some asymptotically hyperbolic 4 manifold.
Okay, all right. Okay.
And then you don't even have a Riemannian structure in the interior. You only have it near infinity. But you'd still be able to prove these compactness results and count the J-holomorphic curves. But that's a talk for 5 years' time, I suspect.
Maybe less, maybe more. But I'm okay with that. Thank you very much for the nice talk.
Thank you.
I do like.
Are there more questions? Or in the room? Alex is probably in a tunnel now. So,
lucky me.
So let me say a few words. Yesterday evening with Laurent, we were drinking beer at least I was drinking a bit, and we were discussing, and we realized that the lectures and all the talks were uniformly excellent. And this is the reason of the success of the school. So we deeply thank the speakers for making the efforts that made this school successful. So we thank you all for that. For those who are online, those who are on the room, and for the others, we will write a small message. Thank you very much. And we really hope that next time we could meet in person. Okay. Thank you. Thank you very much.
And thank you again for Gerard and Laurent for organizing the great organization of this.
So you'll pay the beer today, right? All right.